Hey, welcome back to Fat Mama Physics. In this video, we're going to talk about conservation of energy, followed by a couple of videos that go over examples on the conservation of energy. This video is mostly focused on just highlighting the key things that I need you to know before tackling those examples. And of course, if you do need more elaborations and details, you're welcome to go and on other online sources, videos to catch yourself up. Good thing would be simulations too, which I'll show you in this video as well. Okay, so let's get started. The law of conservation of energy, the idea behind that is essentially energy cannot be created or destroyed, but it can be converted from one form to another. In terms of a system, what that means is I can have energy being converted from one form to another. For example, from kinetic and potential, these two forms of mechanical energy. I may have energy leaving my system in the case of thermal, in which this energy is no longer available, useful for the system. It just leaves the system. Or I may have, say, energy entering my system in the form of work. For example, me pushing a block and accelerating it, therefore it gaining kinetic energy. So it doesn't matter where the energy is coming from, where it's going. Energy is still energy. We can track it. We can track every joule of energy where it goes. And that's the idea of it being conserved. It doesn't mean it stays constant in my system. We'll talk about specific cases. But the fact that it's trackable is the idea of conservation. Just like if I am drinking from this cup of latte, even though the amount of latte in my cup is now less, the latte has gone somewhere. It didn't just disappear. I mean, I enjoyed it, but so oftentimes when you go online, you look at sources, we got to be very careful of the definition of conservation, and oftentimes these sources will get conserved and constant, these two words confused. Okay, when we talk about conservation, we talk about the idea that energy is conserved, not the fact it stays constant in your system. Conserved and constant do not mean the same thing. Hopefully by this end of the video, you will have an idea of the nuances, the subtleties in the definition. So let's talk about it. When I think of energy conservation, I think about two cases. The one specific case that we talk about a lot and which becomes very applicable in our questions is the idea when we have an isolated system. Meaning if I have a boundary with that isolates my whatever's inside my system from the outside, there is no energy exchange within that boundary. No mass, no energy exchange, it is closed, okay? So we call that an isolated system. And when we have an isolated system, the total energy in our system should stay the same, okay? Meaning that there is no work done by non-conservative forces. We will talk about that a little bit later, okay? So when that happens, the change in total energy is zero. If I talk about an initial state of my system and a final state of my system, the amount of energy should be the same no matter what time when I look at my system. And this arrow here, I'm just going to quickly talk about what this means. Imagine this width of my arrow talking about the total energy that's in my system. Okay, so here, if I have here I have an arrow that maintains the same width, meaning the total energy in my system stays the same between its initial and final state. So we can say the here energy total, or the change in energy total, is zero. Another way we can express that is the energy total at some initial state is equal to the energy total at some final state. Okay, so it just means the total energy doesn't change in our system. You might be wondering, what happens if our system is now open, where energy can come in and out of our system in the form of work? So for example, if our system does work on something, it will lose that amount of energy, or if work is being done to our system so that it gains that amount of energy, where that idea comes from, work is equal to the change in energy of our system, in which now the total energy in our system is no longer constant. Now, that doesn't mean that energy is not conserved. Energy is still trackable. It's leaving our system, how many joules that be, or it's entering our system, wherever that energy comes from. The energy doesn't just get created when it enters our system. It doesn't get destroyed when it leaves our system. It doesn't make our system special, okay? Our system's not special. It's not unique. Energy is going somewhere. We still know the energy flow in the whole grand scheme of things, okay? So it's still, energy is still conserved when our system loses that or gains that amount of energy. And oftentimes it gains that amount of energy in the form of work done by some non-conservative force. So what is a non-conservative force, and what does that mean? Well, let's talk about when energy enters, when our system loses that energy because it's doing work on something. And oftentimes it's doing work in the form of friction and leaves our system in the form of thermal energy, okay? And I'm going to write here WNC, where the work is done by non-conservative force. So what is a non-conservative force? Well, first of all, a non-conservative force takes away mechanical energy from our system. So here I have a skateboarder. If I put him on a skate park, drop him or whatever, play, his potential energy is converted to kinetic, but then some of that energy is lost in the form of thermal energy. So the force, the non-conservative force in this case would be friction, for example. It's not the only force, non-conservative force here, but it takes away mechanical energy from our system, mechanical being potential and kinetic. And the other property of a non-conservative force is the fact that it's path dependent. Why? Think about work. Work is force times displacement. If you have a longer path, the force acts for a longer displacement, therefore doing more work. So if I had to compare this with a different skate park, a longer skate park, notice that the proportion here that is lost to thermal is about a quarter in this pie chart here. If I change the tracks to a longer track, and this doesn't really care about the height because we're talking about proportions anyway. So I put him here, I play that, and as he's going, we get some conversion happening. But now, as he's gone to the other side, we have a longer path, and a larger proportion of that energy is now lost due to thermal because he's gone a longer way. Compare that to a conservative force such as gravity. Gravity doesn't care how long you take in between. As long as you get from point A to point B, in which that same vertical drop occurs, it will lose that same amount of energy, or that energy will be converted, say, to other forms. And that's what a conservative force does. Conservative force, path independent. Non-conservative force, path dependent. Non-conservative force takes away mechanical energy from our system, such as friction. So that's why I labeled this here as a work non-conservative force done by non-conservative force. So here, let's just go through this arrow here. We have some initial state in which we have some total energy in our system, and after our system does work in the form of friction, it loses that amount of energy, and it is left with some total mechanical energy final. Okay, so I'm going to write here E total final. So if I had to write this out in an equation, my total final energy here, which I'll write on this side, and I'm just going to write E final because we're assuming all the energy is total. We're talking about total energy of our system. So our E final is our total energy to begin with. I'm going to write initial here. And I'm going to take away the energy that left our system in the form of work. So that's minus WNC, that's the thermal energy that was lost, just like in the skate park, okay? Now, what about if we have work or energy going into our system? What happens then? So here I have some initial state where I have some E initial. Now, here is an example where we have, say, a non-conservative force such as an applied force. If I, say, push this mouse along the table, I apply this applied force, I could go a longer path in which I would have done more work and increasing the speed of my mouse along the table. So that is work done by a non-conservative force such as an applied force. Now, when that happens, energy goes into my system, in which the total energy I have at the end is going to be larger than what I had in the beginning. So in this case, I'm going to add the work done to my system in my initial state over here, and that's going to result in a larger E final, okay? So you might notice that the only difference between these two equations is I have to subtract the work if it's being lost or add the work if it's being added to my system. Energy is gained, okay? So we can then kind of put these two equations together in like this. In which case here I have this initial plus or minus the work done equals our final state and total energy in our system. So that WNC, it is positive if our system gains energy in the term of work, in the form of work, or it's negative if it loses that energy in the form of work. And this is just talking about our system, okay? Now, you might be thinking, oh, how do I use this in a problem? That's not really applicable. Okay, so we can break it down even further. When we talk about final and initial energy, oftentimes we're talking about mechanical energy. Mechanical energy such as kinetic, potential. Potential could be gravitational, can be elastic potential energy. So we can even break it down into more specifics. So let's keep writing here. My initial can be EK initial. It also can be in the form of potential energy. And again, I'm going to plus minus this work being done to our system or not. And then E final, we can write EK final plus EP final for potential energy, okay? And if you want to put in the equations, sure, you can go ahead. Kinetic energy is 1/2 mv squared, and a final and potential energy is mgh if we're talking about gravitational, or if we're talking about elastic, that's 1/2 kx squared. All in your data booklet, you can refer to it there. So then when you use it in a problem, the first thing you might start off with is this following equation that you have here. 1/2 m, we're talking about some mass, and then u for initial velocity, which we use in kinematics in our IB data booklet. So 1/2 m u squared for initial kinetic energy plus mghi for initial. And this plus minus work term might not be in your equation because most of your questions are going to deal with where your total energy in the system stays the same, where no work is being done to your system, or it loses, or your system doing work on something else. So that may not be there. Okay, so then you have that equal to 1/2 m v for final velocity, same thing in your data booklet, squared, plus mgh, where the h is the final height relative to some reference point, okay? So this becomes more applicable for you to use in a problem. Now, if you have elastic potential energy in your problem, you might have to add this term here either to the final or the initial, depending on when your spring was compressed or extended or whatnot, okay? So, but most of the time you'll be dealing with this equation. And in fact, it may not even include the work term, okay? So that is a specific case depending on if your system gains or loses energy, okay? But again, it doesn't matter if your total energy in your system stays constant or not, energy is still conserved. Energy still goes somewhere. It's trackable, not created or destroyed. I thank you for watching. Hopefully you learned something. I'm sorry I made this video a bit too long, but good luck, and hopefully you'll stay for the examples. Great job, everyone. Fat Mama Physics, signing out.